So I'm very happy again on behalf of the organizing committee and the Department of Physics to welcome everyone to the continuation of the Dirac lectures. Once again, we have Dan Holz from the University of Chicago to speak to us.
So thank you all. Welcome back. And I'm going to somewhat pick up where I left off on the previous lecture. And so you might remember that this is where I was. I had presented 170817 and why it's so amazing, and kind of the multi-messenger aspect and the fact that we discovered not only the gravitational waves, but as you can see, the light from a kilonova and the gamma ray burst, and then eventually other emission as well. And so I'm now going to start focusing on the science, some of the things we've learned. So I'm going to spend a little time focusing on what we've learned from this event. And then I'll shift gears and come to the more recent, kind of the present where we're now operating and what we've learned from what we call the third observational run of LIGO Virgo 03. And then I'll end with some thoughts about the future. So, okay, so we had this beautiful event. I mean, really an exceptional event. And there are a bunch of things that came out of it. And I'm going to just try to give you some sense of those things, some of those things, just it's a small subset. Okay, and I'm going to start with, one of the easiest to kind of understand, but also one of the most profound things that came straight out of this discovery. And that's this question, do gravitons and photons travel at the same speed? Really what I should say here is, do gravitational waves and gamma rays travel at the same speed? And that's a very important question. Now, the theory says they should both travel at the speed of light, or the way I like to say it is, gravity has a speed associated with it, and light should travel at the speed of gravity, and they should be the same. And so the question here is, one way to think about, do gravitational waves travel at the speed of light? That's what we want to know. And now you might remember, and there was that video where you had the gravitational waves, you could hear the chirp, and then 2 seconds later, there was the ding of the gamma rays. And so the gamma rays arrived 1.7 seconds after the gravitational waves. And you might say, well, they're obviously slow. And that's a big effect, 1.7 seconds compared to, speed of light. In 1.7 seconds, the light gets pretty far. So that's a big difference. The thing you have to remember is that these waves had traveled for about 100 million years before reaching Earth. And so over 100 million years, you can imagine they were both emitted, they travel for 100 million years, and then they arrive within 1.7 seconds of each other. And that means they're traveling almost exactly at the same speed. And you can put limits. If you assume that really they were emitted at exactly the same time, then okay, that means the gamma rays are slightly slow, but they're slow by a tiny little bit, 1.10 to the 15. Or you could imagine actually the gamma rays were emitted 10 seconds behind, because that's the limit of what our models might say, and then caught up and ended up arriving only 1.7 seconds behind. And then the electromagnetic waves, these gamma rays are faster, but again, only by 1.10 to the 15 or 10 to the 16, something like that. Yeah. Or, what we really think, and this was one of the questions in the last lecture, what we really think is it just took about 1.7 seconds for the shocks to develop. And that delay, the delay is just due to the fact that the gamma rays were emitted slightly slow. Either way, what we have is a bound, and the bound is that gravitational waves and light travel at basically the same speed to 15 decimal places. And that came out right away. I mean, I think a bunch of us in the collaboration, we just did that on the back of the envelope as soon as we heard about the gamma ray burst. And yet that discovery is a major advance because there are lots of theories, and you've probably heard all about dark matter and dark energy. And one of the preferred ways to explain dark matter and dark energy is they're not really there. I mean, it seems kind of ridiculous that a good fraction of our universe is composed of this mystery material. So let's do away with all that, and we'll just assume that gravity itself is broken somehow. It's not what we expect, and we modify gravity, and then we can account for dark matter and dark energy. All those observations are just showing us that gravity is different. Okay, so that's an explanation. In many of those theories, what you end up doing is the speed of gravity changes. Gravitational waves don't go at the speed of light, but we've now shown that they do, and all those theories are kind of ruled out. And so this is a major constraint that happened right away the second, well, 2 seconds after we discovered 1708-17. So do gravitons and photons travel at the same speed? Yes, to 15 decimal places. That's just a very precise constraint. And it's a sort of constraint where before we basically had no constraint, and now we have 15 decimal place constraint. So it just gives you a sense when you have this new way of probing the universe, you can really do radical new things and really make the sorts of measurements that just you couldn't do before. And this is one of the most dramatic examples of that. Just for fun, this is something that I spent a little time working on, which I thought was neat, which is you can ask a similar question. You can ask, do the gravitational waves in the light, do they go through the same universe? Do they experience the same universe? And the way to think about this is what I'm really asking is, for example, does the universe that they go through, does it have the same number of space-time dimensions? And that may sound like a weird question to you, but in high energy physics theories, such as string theory, and then there have been, you might have heard of Randall's sundrum, there have been a whole bunch of variants inspired by string theory, explanations for some of the effects in our universe. And some of those, what they do is they assume that there are higher dimensions in the universe, and then you might have something like all the standard model fields are confined to a brane, but gravity can leak out into a bulk. You might have heard these sorts of words. And the bottom line with all this is there could be other dimensions, and it's possible that those other dimensions are only probed by gravity. And that's hard to measure, especially at large scales. But this event gives us a way to do it. And the way to think about it is, if there are these extra dimensions, the gravitational waves would leak out into the extra dimensions, and the amount of gravitational wave energy, how loud the gravitational waves are, that we measure on Earth, they would be less loud. The volume would go down because the energy has leaked out into the bulk, but the photons, how bright it is, would stay the same. And we would notice that the inferred distances are different. And 1708-17 let us test this. And so we looked into this, and I'll skip over this, but you can ask if you have questions about it. But you can then directly measure the number of space-time dimensions just by comparing the gravitational waves and the light from 1708-17. And so what you find is 4 space-time dimensions right here, 4. It kind of peaks at 4. So 3 space and 1 time dimension, 3 plus 1, which is, okay, you might say, well, you kind of knew that, but we're measuring this on a scale of 40 megaparsecs, so 100 million light years. And we show that on those scales, there's still, the gravity and light both experience 3 plus 1 dimensions. And, it's just pretty cool that we can make that sort of constraint with this one observation. You can also look at, whether the Planck mass varies. That also has effects. I'm going to skip over this just to say we showed that you can constrain it and it doesn't vary. You have lots of experts on the faculty about these sorts of questions and how to think about the standard model, particle physics and modifications, and how you could account for some of the things that we see. So you should certainly ask them if you have other questions about this. But as far as 1708-17 is concerned, everything seems to be as expected from the standard models of particle physics and general relativity. Okay, so do they travel through the same universe? Yeah, they seem to experience the same universe, at least on these scales of 40 megaparsecs. Okay, so you can modify gravity and all sorts of things change. in what follows, I'm going to assume GR is correct and then kind of look at some of the consequences of it. So I'm going to assume that Einstein's theory that describes black holes and gravitational waves is correct. And then we get to infer a bunch of other things. Okay, so the first sort of thing I'm going to talk about is the equation of state of neutron star matter. And this is something I alluded to before, where in 1708-17, we have these two compact dense objects, which we believe are neutron stars. And then neutron stars are kind of the densest matter in the universe. And would love to understand the properties of that matter. When you squeeze it, how much does it kind of push back? And so the relation of pressure and density, these are things that, would just love to know. And it's very hard to replicate in the lab, especially at these sorts of temperatures. So this is a profound question in nuclear physics. And this event gives us one way to probe it. And so this is, again, there are a bunch of details here, which I'm going to skip over. The main message here is that you can come up with a way to describe the effects of the equation of state on these neutron stars. And as they get closer to each other, you might remember what happens is that the gravity from each one causes the other one to deform. And that changes the way they orbit each other and causes a phase shift. And by measuring that effect, we can infer how much they've been squeezed, and that tells us the equation of state. So there is a tremendous amount of information on this plot, and I'm going to kind of gloss over it. It's very subtle when you make these measurements, because the measurements themselves are are quite weak in this one event. Would need many events to get strong constraints. So we're looking for just a subtle shift in the phase as these two things in spiral and merge. And what these sorts of plots show you, and it gives you some flavor for the way these sorts of constraints work. What I'm showing here are you make some assumption about the equation of state, and then you check whether the data is consistent with that assumption. The assumption is given by the priors, which are the filled in areas. So like this gray bump here is a prior, and then you do the analysis. And in the analysis, you can use a bunch of data. You can use pulsars, you can use the gravitational wave data. There's this very interesting satellite experiment called NICER, which has been producing beautiful data. And we can incorporate all this data, and then we end up with posteriors, our measurements, our estimates of the quantities. And if those posteriors are different from the priors, then the data is informing us. It's telling us, no, it's not what you thought it was. It's actually over here somewhere else. And that's a sign that you're actually making a measurement. And so, although we're not making much of a measurement here at below saturation density, kind of the ultimate nuclear density, and as we go even past that nuclear density, we start to make more interesting measurements. Here's another way to show this. This is the classic pressure versus density. This is an equation of state plot where we're showing the equation of state. And here we've used chiral EFT, which is one model for what this equation of state might look like. It's a way to calculate it. And we show that by using this chiral EFT priors, you narrow the equation of state, and you also make a slightly informative constraint. There's a lot of detail here. It's quite technical. And actually you have so many experts on nuclear theory and nuclear experiment. They're much more knowledgeable about these sorts of things than I am. And so, I encourage you to, if you have questions about this, there's so many people on the faculty that you could reach out to and discuss this with. It's really fascinating. And it's one of these things, again, this is just our first event. And yet we have it's weak, but we have these preliminary constraints. As we go forward, we'll get more and more events. These constraints will really sharpen up, and we'll be able to tell you at these extreme densities, what happens to this material. And that'll be fascinating, it'll teach us a lot about fundamental nuclear physics.
Can I interrupt for a second, Dan?
Oh yeah, please.
So, I'm sure that you probably heard that chiral EFT is a very popular theory of nuclear physics, but essentially because it's chiral EFT, it's very hard to extrapolate to very high densities.
Yes.
So do you have any comment about that?
It's what we can say is, the data is not inconsistent with some of those extrapolations. But we have, some other approaches, and here, so I kind of, there's this, so what we've tried to do is be somewhat agnostic to the, specific theories. So, you can do some quantum Monte Carlo, calculations using a range of theories and then see what comes out, or many body perturbation theory, or whatever your favorite approach is. What we find, unfortunately, is that if you don't put in a prior, so if you don't assume chiral EFT as your prior, and you just complete, the agnostic prior here, what we call agnostic analysis here, has only that the speed of sound in the neutron star should not exceed the speed of light. That's our main constraint. And when you put in that, you get these much weaker bounds. It's perhaps less interesting, but we haven't had to do any extrapolation at all. And so, what's nice and kind of what we emphasize in all this work is, if you have something you prefer, it's very easy to incorporate it, and then we can redo this analysis. In all cases right now, it's quite weak because the constraints are weak, just because we just don't have enough information. But as we'll go along and get more data, more sources, we'll do a much better job.
Thank you.
Is that helpful?
Absolutely.
We can discuss this more. I mean, there's a lot to say about the details and how this works. And so, for example, this should not be viewed as chiral EFT solves everything. That's definitely not the message here.
Thank you.
All right. So I'm going to spend a little time on the Hubble constant on standard sirens, and then I'm going to switch gears and talk about O3. This is just another thing that came out of this discovery of 1708-17, and it's something I was extremely involved with, and I just think it's a very elegant story of the power of these sorts of multi-messenger observations. So I'll just remind you that the Hubble constant is the rate of expansion of the universe today around us. So you look at galaxies, so we know the universe is expanding, and so galaxies that are near us are moving away from us, and the rate at which they're moving away is proportional to how far away they are. So if they're further away, twice as far away, they move away from us twice as fast, and that proportionality constant is called the Hubble constant, and that's one of these profound, important numbers describing our universe. And it relates now, if you could measure this precisely, combining it with other constraints such as the cosmic microwave background gives you insight about the dark energy and dark matter and various other things. It's something would really like to pin down, and have been trying to pin down essentially since Hubble first started to measure this in the 1920s. So we're about 100 years down the road, and we're still trying to nail this down. And the reason there's been a lot of discussion about the Hubble constant lately is because what's happening is what we call local measurements, things like type 1a supernovae, are used to measure the Hubble constant. You might remember that the type 1a supernova measurements discovered that the expansion of the universe is actually accelerating. So as you go farther and farther out, you start to see that it's no longer linear, the curve bends. And if you analyze that carefully, you find that in the recent universe, the expansion rate has been accelerating. That's extremely exciting, and that's evident. That's the evidence for dark energy. When you do measurements of those objects, you end up finding Hubble constants which are slightly high, around 72. When you use a cosmic microwave background, which is a distant measurement at the edge of the universe, this is the baby picture when the universe was only a few 100,000 years old, instead of 14 billion years old as it is today. When you do the comparison, the early universe measurements of the Hubble constant are actually low when you infer the Hubble constant from those. So there's a discrepancy here, and that's caused a lot of excitement and confusion and consternation in the community. So this, depending on whom you ask, either this, these measurements are starting to kind of come together, or they're moving apart. I think they're generally considered to be about 4 sigma away now, which is quite a bit. And it's hard to imagine either of them moving significantly, because people have really studied all the possible systematics. There just seems to be a discrepancy, and we don't understand why. What's interesting about that is it could be a sign that there's something profound about our universe we don't understand, and that this standard model of cosmology, which links the cosmic microwave background to everything we know today, that there's something happening in between there that is not accounted for in the model. And so this could be a clue that, it's going to break open our whole model of cosmology. So people are very excited. On the other hand, it could be, and my guess is this is probably what's going to end up happening, it could just be some systematic, some very tricky systematic, or maybe a few systematics, maybe in both measurements. And this one actually comes down a little bit, that one goes up a little bit, and they meet in the middle or something. We don't know. Right now, we don't know. And a lot of people are working on this from many different directions. Okay, so that kind of sets the stage. The bottom line is we'd love to have a very clean measurement of the Hubble constant. And I wouldn't be telling you all about this if it weren't that gravitational waves could help with this. And in fact, there's this thing called the gravitational wave standard Siren, which is specifically a way to measure distances using gravitational wave sources that's extremely clean and direct. And what you do here is you listen to how loud the source is and what the sound of the chirp is, how it evolves. And from that, you can figure out the distance directly. So it's a direct way to measure the distance, and then if you could find a counterpart, you could also get redshift. So let me first just focus on the distance part. Measuring distance is very difficult in cosmology. You can't just run a tape measure out and figure out how far something is. So to measure distance, what is generally done is you use something like what's called a distance ladder, where you measure local distances and then you kind of build on that, and you ladder your way out. You build on, you have, say, 4 different methods, and each one kind of takes you further and further out until you get way out into the into cosmological distances. The gravitational wave sources, it's different. It's as if you just ran a tape measure out 100 million light years away and just said, this is how far away that source is. It's remarkable that this could be done. So this is something that's very, very powerful. The calibration here is just provided by the theory of general relativity. The calibration is provided by general relativity. It's very clean. You just get this distance. What you don't get is a redshift. So usually with cosmological measurements, what is clean is the redshift. You can just measure a spectrum and you get the redshift. For gravitational wave sources, you don't have a redshift. It's scale free. You can think of it as there's no, there's the Planck constant gives you special scales. So you get these emission lines for electromagnetic sources. In gravity, you don't have that. And so there's no preferred scale. Black holes can be small or big. The theory doesn't care. So if you want to actually get a redshift as well, the redshift tells you the relative size of the universe. If you want to get that, then you need some other measurement. And so to use a standard Siren, you use the gravitational waves to give you distance, and then the electromagnetic waves to give you redshift. That's the ideal. And needless to say, 1708-17 provided that. Here's some details on how this works. I'll skip that. Just to summarize, the way this works is the redshift gives you, if you like, the recession velocity. It's like a Doppler shift, and that is eventually related to the relative size of the universe. What redshift really measures when you say, oh, something is a redshift 1, what that tells you is that the universe was half as big when the light was emitted as it was today. That's something that comes straight out of general relativity. The distance is related to how long the light is taken to travel. If you assume it goes at the speed of light, then distance is related to time, and that tells you the time at which this light was emitted. And so now you have the size of the universe as a function of time, and that's obviously a very interesting quantity. It's kind of the evolution history of the universe. Okay, anyway, if you can measure velocity, redshift, on the left, and you can measure distance on the right, you can infer the Hubble constant. That's the way this works. 170817 is the perfect standard siren. It was very loud in gravitational waves. We got a very nice measurement of distance. In addition, we had this optical counterpart, which I talked about, and you can see an image there, and there's a galaxy right there. And I actually just, the first time I did this, I just Googled the galaxy and got the redshift. And eventually we went and did our own measurements and made sure it was very precise. But I mean, it was trivial. So we had the distance, and I could just pull up the redshift, and we could measure the Hubble constant. And you have to understand, this is something that people had talked about. It was first suggested by Bernard Schutz in the 80s. And then I did a bunch of work on it, primarily with Scott Hughes, a frequent collaborator, in the 2000s. And, I had spent, some fair fraction of my career writing papers saying there could be a standard siren. LIGO might actually detect something. That would be great. It might be a short gamma ray burst. I wrote all these papers, and people were telling me, it's never going to happen. This is a fantasy. First, LIGO has to work. Then you have to be lucky enough to detect a binary neutron star. Who knows if we'll ever detect those? It could take years. The predictions at that point would be that it wouldn't happen from now at least another 5 years. And then you'd have to get a short gamma ray burst. What's the likelihood of that? And then everything has to, forget it. You're wasting your time. That was the message. And then 170817 happened. And in fact, 170817 was too good. It was so loud. And the reason it was so loud is because it was quite close. And it was so close that you actually had to worry about some other details, which I won't get into now, but you can ask me questions about. But that's fine. We kind of compensated for all this. And after all this, we could produce a measurement of the Hubble constant just with this one event. And this is what we found. And for me, this is one of the most beautiful plots in science, because it's a measurement of the expansion of the universe, the rate of expansion of the universe using gravitational waves and compact objects predicted by general relativity, these neutron stars, which in themselves were also controversial at the time. All this stuff wrapped all together to measure the expansion rate of the universe. And this is what we get. And you can see, unfortunately, I've lost my mouse, so I can't point to it, but there's a clear peak, and the peak is right around 70, which happens to be right smack in between these two competing measurements. The errors are still large, but you have to remember, this is the very first time we've made this measurement. It's one source. And the fact that we're here at all, the fact that all of this stuff works, that general relativity works, and that the measurement is consistent with what all these other methods have found, I think is truly remarkable, perhaps miraculous. I mean, science really works. So this was just our first source, and I think it's already quite exciting and promising.
Is there any way to reduce the spread, or do you need another source, actually, another event?
Yeah, so that's a very interesting question. So the question is, how can we do better? And in this, the question is, so you might look, there are a few very interesting aspects of this. I think one thing that should immediately draw your eye is the fact that this is not a Gaussian, that there is a clear tail as you go to high Hubble constant values. But then it's kind of sharper at the low Hubble constant values. And the reason for that has to do with what's called the distance inclination degeneracy. And what that means is gravitational wave, if you have a binary, so here's my binary, if you look at it edge on, so you're in the plane of the binary, it's actually slightly less loud than if you look at it face on, and the whole binary kind of, you're looking into the heart of the binary directly. And so the inclination changes the amount of gravitational wave energy, how loud it is. And so if you don't know the inclination, you're not quite sure what the distance is. So what you really like to do is be able to measure the inclination as well, and then this would be much narrower. And so there actually have been at the end, if you want to see more, I can show you some plots showing the inclination measurements. Those are, what you do is you can use different ways to infer the inclination of the system, and then you can use that and constrain this better. I'll just give one caveat on that, is that what's beautiful about this plot is just general relativity. That's what's measuring the Hubble constant. If you add inclination, now it's general relativity plus a lot of very complicated astrophysics to infer inclination to measure a better plot. And that's fine. I mean, then we improve our measurement, but the goal here is to really reduce systematics and to have as pure and clean a measurement as is possible. And so I worry that if you do too much work with inclination, you introduce additional systematics. So that's one way to do it, is to just further study this, improve inclination, for example, and narrow this plot. The other way is to have more sources, and that's what I was going to show in the next video. So let me just show that. And this is just, this is a video put together with my former graduate student, Maya Fischbach. And what she did is she just Monte Carlo'd a bunch of discoveries. We have our first event, now let's get some more, and let's see what happens as we get more, and just kind of a visual way to see that things converge, and they converge reasonably quickly. And so what you see is you very rapidly get a strong peak, and then certainly by 50 events, you're already at a couple percent, and then it gets narrower and narrower. And so that's what happens. And part of the reason it happens, and it actually happens quite quickly, is because of this non-Gaussianity, because of the fact that it's not symmetric. So if you have a bunch of events and they have tails, sometimes the tails go to high Hubble constant, sometimes they go to low Hubble constant. If you think about that, that actually converges faster than if you just have a bunch of nice Gaussians. And so you actually find that even with just a few events, 10 events, 20 events, we'll have percent level measurements of the Hubble constant. So it's very exciting and very promising if we get the events. Right now, we still only have one multi-messenger event, so there's a ways to go, but predictions are that in the next few years, as we improve the sensitivity, we'll get many more, and we'll end up having a very precise measurement of the Hubble constant. And this is just a plot to show that we're probably not that far away. A few years, it depends. The big uncertainty here is the rate. And so that's still something we haven't nailed down. And I can talk a lot more about this. And I'll just mention as an aside, this number, it's not just, there's this discrepancy and it'd be nice to resolve it. That's certainly the case, but it's also a precise measurement of the Hubble constant constrains a bunch of other things about cosmology, including the equation of state of the dark energy, which is down in the lower left on this plot. So this really is a profoundly important number that we need to nail down, and this is one way to do it. Okay, there are a lot of systematics. The main systematic, the thing that I most worry about, it's not the usual things in astrophysics of like type 1a supernovae, and we don't understand how it depends on host galaxies or metallicity or who knows what. The main systematic here is the actual response of our detector. How when the mirror moves, how well do we measure how much it's moved? And getting that to 1% turns out to be hard. And I can talk more about ways to address this. The expectation is we'll be able to do better than 1%, and there's some very clever ways to improve this, but that's something that has to be nailed down if we're going to use this to really make profound statements about cosmology. I'll just mention this as an aside, which is I think this is also very cool and just very different, and something that people, you couldn't have conceived of this even 5 years ago, which is that this event, 1708-17, was so loud that you can actually use the event itself to calibrate the response of your detector. I was just talking about this. You have to know that you've calibrated the motion of the mirror properly. And because this event was so loud, you can actually watch the event evolve over frequency. And if there was some weird calibration where you're at this frequency, your response is different from this other frequency, we would notice it because the waveform wouldn't look right, and the waveform looked perfect. And so we can constrain the performance of the instrument using an astronomical source. So you have to remember, for the last 100 years before 1509-14, people thought we would never detect anything, that it's just gravitational waves are too weak. And even in the years immediately preceding our first discovery, 1509-14, even just before that, very prominent people in the community were telling us, it's not going to work. It's just too hard. 1 part in 10 to the 21 is not possible. You remember those early plots, shaking a star the width of a human head? It's just, you're not going to be able to do it. And now we're actually measuring the performance of our instrument calibrated to an astronomical source of gravitational waves. It's incredible what's happened and how much things have changed just in a couple of years. Okay. So that's it for 1708-17. That's all old news. I'm now going to shift gears and talk about some of the more recent results. And my understanding is I have about 45 minutes, but maybe I'll end a little early so there's time for questions at the end. Does that sound good?
Sounds good.
Okay, great. Okay. I guess maybe I'll just show this to give a sense of this. So I think it's not often that we have a whole new field. And so what has happened is just in the last, since 1509-14, there's the birth of this new field. And what it means is there's this kind of bonanza of results and things to work on. And so this just gives you some sense. So these are just papers I've written in the last year on all different aspects of this field. And I'll talk about, I'll just give, my plan is to just talk briefly about some of them, just to give you a flavor for the sorts of questions you can ask and the directions that you can go in this brand new field. It's a range from understanding how these systems are formed, the binary neutron stars and the binary black holes are formed in the first place, to how you infer, and we talked about this, equations of state, measuring the expansion scale and cosmological things with standard sirens. So that's some of the things. This is just in the last year. Here's a bunch of other stuff. There's issues of the populations and, what are the distributions of mass ratios or spins and what do those teach us? There's a lot of information about gamma ray bursts that is incredibly interesting. There's this binary host connection, which I won't have time to talk about, which I think is fascinating, which is where you use the host galaxies of the binary systems and you learn about the formation of the binaries from properties of the host galaxies. And even with 1708-17, you can do something interesting already. There's just a lot going on. There's also lensing of gravitational waves, which has gotten very interesting just recently. And I can talk about that if there's interest. So what I'm going to do is just pick a few of these and kind of discuss them in more detail. First, let me just give you the overview of where we're at. So right now, we're at the end of the third observing run of LIGO Virgo. That ended in March, slightly early because of the pandemic, but we got most of our data. We issued about 60 alerts. So what happens now is as soon as there's a gravitational wave event, and we feel reasonably confident about it, we send out an alert so that astronomers can point their telescopes, hoping for another 1708-17, another multi-messenger source. So we are much more sensitive in 03 than we were in 02. We've gone a lot more. In 02, we had 10 binary black holes and 1 binary neutron star, and in 03 we've already had about 60 alerts. We published, actually, it's not 3, we published 4 discoveries. We had our 4th one announced last month. And in the next, I think now it's within a month, we're going to publish the catalog. The expectation is that in the next month or so, we'll publish our catalog from 03, which will be a list of all the events we've discovered and what their parameters are. And what they teach us, the kind of what that population teaches us, and we'll have tests of GR, and there'll be a lot of stuff. I was hoping to be able to discuss that a little bit in these lectures, but everything's been delayed, and so just keep your eyes peeled for that in the coming month or so. Okay, so what I'm going to do now is kind of go through the 4 discoveries that we've announced so far, and I should say what we do is we cherry pick the data. We get all these events coming through. We have to choose what to focus on to write papers about early, and we pick the ones that we think are interesting. And interesting here generally means they're not like all the things we've seen before. And so here are some examples. So the first thing we published was 1904-25, and this was a binary neutron star event. And so this was incredibly exciting. It's another binary neutron star. Unfortunately, the sky position was quite large. We didn't localize it all that well, and we weren't able to find a counterpart. People pointed their telescopes, but there just wasn't. It's just too much of the sky. What was interesting about this event, I mean, first of all, it's another binary neutron star, but also the masses of the neutron stars are large. It's the total mass was about 3.4 solar masses. That's unusual for binary neutron stars, at least the ones that have been found in other ways. So that tells us something. Either there's something about the binary neutron star population we don't understand, or maybe the gravitational wave sources are for some reason slightly different from the other. There's something interesting there, something that needs to be understood. It's just an exciting event. It kind of tells us the population is not as simple as we might have thought. Okay, so that was the first one. Then there was 1904-12. This is a binary black hole event, but what was weird about this one is that the 2 black holes were very different masses. The bigger one was 30 solar masses, like a lot of the ones we've seen, and the smaller one was 8 solar masses. The mass ratio is not 1. It's clearly, it's a ratio of, maybe 1 to 3, or there are errors on this, so 1 to 4, something like that. It's not 1. And all the previous binary black hole events that were detected to date at this point have had ratios of 1. And in fact, I made a big fuss in some papers saying, they're all consistent with having mass ratios of 1. That's really interesting. And then this black hole comes along, this binary black hole comes along. It's not a mass ratio of 1. That is some clue as to how these are formed. We're not sure exactly how to interpret it yet, but it means if your theory only says, and some theories do say, all black holes that are made in this way, like there's this chemically homogeneous channel, in general, those black holes have the same mass. This black hole system could not have been made from that channel. So it's
Can I
interesting.
ask something about
Yes.
this? So what is a sensitivity bias? So do you have a better sensitivity if its ratio is 1, or doesn't really matter?
Yes, great. Yeah, so there's a great question. So yes, so our sensitivity does depend on the mass ratio, and we are more sensitive if it's 1. And so you have to, when you analyze your data and infer the population, like the distribution of mass ratios, it's very important that you take that into account. And that's often something that's missed. And that's a general statement, and I think it's very important. So I'm going to kind of reiterate it so everyone understands what we're talking about. So the question here is, okay, we detect some things with our gravitational wave detectors, and I say, oh, look, we have this black hole, binary black hole, and this binary neutron star. And now I want to make statements. What do binary black holes in the universe look like? To make that next jump, you have to understand what you're sensitive to. And so, for example, in our case, we're much more sensitive to big black holes than we are to smaller black holes, because those are much louder. And so we see big black holes much farther away. We see them to a much greater volume of the universe. So if we see the same number of big black holes as small black holes in our detector, that means the real number of small black holes must be much, much larger, because the big black holes, we're seeing them much farther away. If there are small black holes out there, we don't have the sensitivity to them, but so you have to take that into account when you infer your rates. So the sensitivity of your instrument is key. And so we spend a lot of time characterizing that. Now, what's interesting about the gravitational wave sources in general and gravitational wave astronomy is that we can do that. We understand our instrument, we understand what GR predicts, and so we can do this analysis and figure out what the sensitivity is, how it depends on masses and spins and mass ratios and all these other things, and incorporate that into our analysis, and that's what we do. Getting that all right has taken a while, but now we have a fairly robust formalism to do that, and we do incorporate all that with all these things. So that's a very important point. This have to do with selection effects and population effects. So it's very important to incorporate that. So excellent question. Yeah. Here's the next thing we discovered, 1908-14. This was one of the first really surprising things we discovered, which was it's a binary system. The more massive object is a black hole, but the less massive object is 2.6 solar masses. And I'll talk more about this, but 2.6 solar masses is pretty big. So it would have to be a really big neutron star, the biggest neutron star we've ever detected. Or it could be a black hole, but then it's the smallest black hole we've ever detected. We haven't detected black holes confidently below about 5 solar masses. So either this is an unusually large, the largest neutron star ever, or the smallest black hole ever. We're not sure which. We don't see any, we're not sensitive because of the frequencies and because of when you have a big companion, by the time you start getting squeezed, you fall into the black hole. So in this case, if it were a neutron star, it falls into the black hole too soon, and we don't see the effects of the squeezing on the equation of state. So we just don't know. Is the smaller thing a black hole or a neutron star? We have no idea, and nothing was seen. There were no flashes of light, which would give us some clue. So we don't know, and that's where we are. Either way, it's fascinating. Now you might say, well, okay, that event is gone. Will we ever figure this out? For this particular event, we can never definitively determine which way it is, but for the population, we'll be able to say, as we see more of these, are they consistent with kind of a population that goes to more and more massive black holes? Or is it consistent with neutron stars, and the most massive neutron star is around 2. We'll find out. It'll just take time, but that's part of what's exciting about this new field. And now I'm going to get to the event that we announced last month. This is 1905-21, and at least for me, this is the most interesting event we've seen. So, and what I mean by that is let me just say, it's the most surprising event we've seen. Everything we've seen so far, everything I've talked about, 1509-14, 1708-17, and all the rest of these are all events that were predicted. We didn't really know the rates, we didn't know how soon they would happen, but the theory said events like this should exist. Theory fairly robustly said that this event should not exist, and let me explain why that's the case. So this is 1905-21, and this is the merger of what we think was an 85 solar mass black hole with a 65 solar mass black hole. And the theory of how black holes are formed, how they're made, says you really can't make black holes that are around 85 solar masses. That should be difficult. And that has to do with this pair instability mass gap. So let me explain these mass gaps, because a lot of the interesting things that are going on in this field right now have to do with these mass gaps. So this is a picture I've stolen from a postdoc at UChicago, Jose Maria Esquiaga, and I'll talk more about why he made this picture a little later. But what this picture shows is what we think is the population of black holes. And on the lower end, you can see this gap, the neutron star gap. And so that's this question of whether, what is the lowest mass black hole? And, there's some evidence that the lowest mass black hole is about 5 solar masses. The biggest neutron star is expected to be about 2.5 solar masses. And so there's a gap between 2.5 and 5. That's that neutron star gap. So whether or not that exists, for sure, we don't know. but there's some evidence for it, and it's something that we should be able to figure out, or at least further inform with LIGO Virgo detection. Then you have the stellar mass black holes, so this blue population, and then there's this pair instability supernova gap right in the middle. And that gap is due to this pair instability supernova mechanism. And the idea here is most black holes, we think, are formed where you have a star, the star evolves and eventually dies and collapses. The reason it collapses is because it runs out of nuclear fuel. So the story is that, as a star is burning, it's doing fusion burning, so it's burning hydrogen, and you go along, then you produce, maybe helium, and then there's, you have carbon and oxygen, and you just continue down until you get to iron, and you can't burn iron through fusion anymore. And so the whole process stops. And kind of one simple way to think about it is you run, since you're not burning, you're no longer hot, and the whole thing starts to collapse. And then maybe you get a neutron star at the center and the whole thing explodes, or maybe you get a black hole and the whole thing collapses, or there's a lot of trickiness there. But that's the general picture. And that's the way, if you have a big enough star, you end up with black holes at the end. However, if the star is really quite big, it gets so hot in the center that there's a phase where you start making E plus E minus pairs. So you start spontaneously producing pairs, which causes you're taking sort of energy away from the star to make these pairs, which means the star starts to collapse, it gets even hotter, and you make more pairs, and this whole thing runs away, and you get a tremendous explosion, and nothing is left behind. And that's called a pair instability supernova. And so it's been predicted that if that happens, you end up with no more black holes. And so there's a range, and that range is roughly speaking between 50 and 120, where theory said you're not going to make any black holes there. So that's the prediction. And then beyond that, there are these things called intermediate mass black holes. If you have a big enough star, if it's really humongous, then it just collapses to a black hole. The pair instability supernova doesn't happen, and the whole thing just collapses. And so you start having black holes again. So that's what the theory said should happen. And then along comes 1905-21. And just to give you a sense of this, so this is what I'm showing here are our best guesses, analyzing the data for M1, the mass of the more massive black hole, and M2, the mass of the less massive black hole in this 1905-21 system. And I'm just going to kind of mark out where the pair instability, where the theory says black holes don't exist. And what you can see is at the top, the entire range of M1 is ruled out. This black hole should not be there. And for M2, almost everything is ruled out. The bottom right corner, which is lower masses below about 50, is still okay. But everything else, which is the bulk of the probability, is ruled out. So this is an incredibly surprising event, and we'd really like to understand it better. So you can ask, what's going on? Like, what's the story? And there are lots of possibilities. You could have made this black hole out of smaller black holes. This is a very popular explanation right now. Maybe you made this out of two stars merged, and if you can merge the stars just right, you could end up with a star that doesn't go through the pair instability phase and just collapses to a black hole. Or maybe there's some funnier things going on, primordial black holes, or we're actually misinterpreting and there's lensing or something else. We don't know. We don't know. It's very exciting. There's a lot of activity. This event is, it's only just over a month old, and there have been a lot of papers and a lot of people trying to figure out what's going on. So I'm just going to tell you my favorite theory for what's going on. And so this is some work I did with Maya Fischbach, that's a graduate student in Chicago. She's now a postdoc at Northwestern. And the idea here is pretty simple. And it's related to some of the things I've alluded to previously, which is that you have a prior, whenever you do analysis, you have to have some assumption about the population. And when we presented, when LIGO presents the mass values for 1905-21, those mass values are assuming nothing about the population, saying we have no idea what the masses of these binary systems might be. So what Maya and I did was say the following. You might remember that there's that tail, this tail in the bottom right here, which says that the lower mass system could be okay if it actually is slightly lower mass. And that's completely consistent with the observations. So what we said is let's actually use what the rest of the population tells us is the case. And I should say, it's an important point. The population tells us there's definitely this gap where you see a bunch of black holes, and I'll talk more about this, and then suddenly they disappear. And so we know that there's some gap. So if we use that and we analyze this latest event in the context of the rest of the population, we find that sure enough, the lower mass one is below the gap. And what's interesting is if you do that, you find that the more massive one must be above the gap. And this is one way to show this. It's kind of a busy plot, but it's showing M1. Again, the x-axis is the mass of the more massive one. The y-axis is the mass of the less massive one. And what we show is that when you do the analysis using the rest of the population, your object ends up in the green contours. And the bottom right section, the white part of this box, not grayed out, the white part in the bottom right, that's the okay thing from the pair instability supernova theory. And you find that actually it's perfectly okay. What's happening is your binary is splitting. The lower one is going below the gap and the higher one is going above the gap. And that's totally fine with theory. And that's what naturally happens if you assume these are part of a population. So we think this is a very interesting. Now, if this is right or not, we don't know. We'll need more detections, but it's very suggestive that instead of having two objects in the gap, both of which really put pressure on our understanding of how black holes are formed, what you can do is have one object below and one object above, and that actually fits more naturally with everything. This gives you some sense of some of the questions and some of the tricky aspects of doing these analyses. I just show this part of the parameter space is totally fine. Okay, so now I'm going to talk just a little bit. I'll probably spend another 15 minutes or so, and I'm just going to talk about a few other things, interesting projects, many of them related to what I've just been talking about. And one is this pair instability supernova standard Siren cosmology. And I think that this, again, it kind of touches on some of the interesting things we've learned so far about our populations. The first is that LIGO is definitely missing big black holes. And the point here is something that, again, I did with Maya a few years ago. We looked at the distribution of the black holes that LIGO was seeing. And as we mentioned, I mean, the question about selection effects was very relevant to this. LIGO Virgo, our network, is extremely sensitive to big black holes. We see them much farther away. And so the fact that the biggest ones we've seen, certainly when we wrote this paper, the biggest ones were like 30 or 40 solar masses, when we could be seeing things at 100 solar masses. The fact that we weren't seeing those much more massive ones is a clear sign that the population is cutting off. And we showed, I mean, this paper basically shows that what I like to say is absence of evidence is evidence of absence in this case. There are no big, the population cuts off just the way is expected from pair instability supernova theory. Okay, so that's here's another way to see this. And you can, as you do the analysis of the data using using everything, this is at the end of O2, all the data at O2, you can see that it bends over towards the right. There just aren't enough events. We haven't detected enough events at very high mass. We know the population must be tailing off. It might be a taper, but it's definitely decreasing. There's no question about that. What we noticed, and this is work with Will Farr, what we noticed is that, if you have this taper, this cutoff, that feature will redshift. As you go to a higher redshift, all the masses will redshift and they'll look larger. And you can watch that feature redshift And by measuring that redshift, you can by measuring that feature, you can infer the redshift. And now you have an independent way to measure redshift. You no longer need an optical counterpart. And so you can get redshift just from the population. You get distance from general relativity. Now you can measure cosmology just like we did with the standard sirens in 1708-17, but now we're getting the redshift from the population. It's a totally different way to get redshift. And we showed that this works extremely well and that we get measurements of redshift at the percent level in these small bins out to high redshift. And so this is extremely powerful. I could talk more about this. This is just a graph showing you the edge. And I think this shows you how well we do. This is not just the Hubble constant now, this is the full expansion history of the universe as a function of redshift. And we show that, you know, with 5 years of advanced LIGO data, you actually are constraining this extraordinarily well. So not just the Hubble constant, which is the value of redshift 0, but out through, for people that think about this stuff, the universe, as it expands, the role of dark matter and dark energy have flipped. In the early universe, dark matter was all that mattered, as it were. In the late universe, dark energy is taking over, and now we see the universe's expansion is accelerating. This method probes right across that transition. So it's very exciting. This assumes the feature has no systematics, and so there's a lot of issues here. To do it well will require a lot more study. But it's a method which just no one could have thought of even 5 years ago. And now it's something where I think people are starting to take it quite seriously. And it could be one of the more interesting things that comes out of gravitational wave observations in the future, because now we're using binary black holes as standard sirens to measure cosmology at high redshift. And we're going to get thousands of binary black holes. So this will become very, very powerful. Okay. So my plan now, maybe what I'll do is I'll spend 10 minutes and give a few more highlights, and then I can stop for questions. Does that sound okay? Or I could, or maybe I'll make it 5 minutes to leave plenty of time for questions. And then, okay. And then what I'll do is I'll highlight something if people want to hear more, you can just ask me to go back. And again, my goal is just to give you some flavor for some of the sorts of questions and some of the sorts of things we're learning from gravitational wave astrophysics so far. So one question is, okay, we're measuring these systems. Do we have any evidence that the rates of mergers are evolving with time? And so we have these models which say these binary black holes are being formed from binary stars, say, that evolved and merged. If you ask what's the rate of stars, when a star is being formed, there are a lot more stars being formed earlier in the universe. The universe used to be a lot more exciting than it is today. The number of stars being formed now is kind of starting to taper off in the entire universe. And so you might naturally expect that the rate of binary mergers, there are a lot more of those happening earlier in the universe, earlier in time, and nowadays that's starting to taper off as well. So we thought, well, we'll go look for this, and we did. And as of 2002, there was very little evidence. We show you we can constrain this. We should be able to constrain this quite soon, but so far, we don't know. But this is something where I think going forward, we're really going to be able to constrain this, and that'll teach us about the relation between stars and black holes, and that's going to be fascinating. It'll help us figure out how these black holes are being made. This is, this is kind of interesting. This has to do with, I think it's interesting. We just make the following point. If you take two black holes and you merge them, it's very hard to get rid of that orbital angular momentum. And so you have two black holes, they're orbiting. That's a lot of angular momentum. The final black hole inevitably ends up spinning. And it spins at what's called a dimensionless spin parameter of about 0.7, which is spinning quite rapidly. So this black hole is like a top, it's spinning quite quickly. Spin of 1, you can think of it very roughly speaking as then, it's spinning, the surface is sort of spinning at the speed of light quite like that, but so there's a limit to how fast a black hole can spin, and we're at 7/10 of that limit. If you make a black hole out of smaller black holes, even if the smaller black holes are spin, no matter what you do, you're going to end up with something close to 0.7. And so, we said, oh, this is an interesting test. If you want to know, are your black holes being made from smaller black holes? Here's the test. And now, in part because of this latest discovery in 1905-21, everyone's trying to make bigger black holes out of smaller black holes. I think this test is going to become increasingly interesting and relevant, but we'll see. So it's just it's kind of a robust feature that comes straight out of general relativity. Okay, I think maybe I'll talk through this and I'll conclude after this. I think this is also a kind of neat sort of measurement, and it's a different sort of measurement from the things I've talked about so far, which is there are really two different types of sources that we can talk about, and I mentioned this briefly in the last lecture. You can have these compact binary sources where you have one binary system and we measure the gravitational waves from that, and we say, oh, look, there was a binary black hole, it was over there, and it has these parameters. But there are a lot of binary systems out there, and as you go to higher redshift, you get many, many, many. Now, they're all not quite loud enough for us to hear individually, but we can hear the background hum from all of them, and that's what we call the stochastic background. So this is the astrophysical stochastic background from all the binary systems in the universe. So that's something we've been hoping to detect, and we have not detected it yet. Now, what's interesting is I'm going to pull a bunch of different things together. We have not detected this background hum. We have detected a bunch of binary systems at lower redshift. That's all the things I've been telling you about. We need those two statements to be consistent. So if you assume that the rate that the population increases with redshift, just like all the stars do, and there are a lot more binary systems at high redshift, eventually you get to a point where we really should have detected that hum already, and we haven't. So we know that there can't be that many binary systems at high redshift, so the rate at which these systems are increasing is constrained. So by comparing the non-detection of the stochastic background and the detection of of the low redshift CBCs, we can constrain the rate. And so the green plot here, the one on the left, shows all the possible rates given what we know about our system so far. And you can see that it could be increasing dramatically or decreasing dramatically, we don't know. And then on the right, we show what happens when you include the fact that we haven't heard this background murmur of binary systems. Then we know it can't be increasing without bound. It's actually cut off, and it's a fairly sharp cutoff. And this will only get more interesting with time. And I think it's remarkable that the non-detection is already telling us something interesting about the rate of evolution of binary systems. So it's just another example of these very powerful things that are coming out, which we had no information about before. I'm just going to end with a couple more slides about my group. So this is the UChicago LIGO group. So a lot of the work, especially in this later part of the talk, was done by the people pictured here. So there's Jose Maria Esquiaga and Reed Essick. They're both postdocs in the group. Bob Wald is, a faculty member in GR and was actually my PhD advisor. And a very valued colleague, and he's part of the LIGO group, and especially on issues of testing general relativity, he's been had quite a lot of impact. Amanda Farah is a current graduate student in the group. She's been working on gamma ray bursts. Maya Fischbach, I worked on a number of the papers I discussed. She is now an Einstein Fellow at Northwestern, and Zohair Doctor was a former student in the group, and he's now a postdoc at the University of Oregon. I'll also just mention that LIGO, especially the first part of the talk, was focused on LIGO events and LIGO data, and the LIGO results. And this is just a plot of it's just showing the logos of the many institutions that are just on the LIGO side. There's also Virgo, which also has a ton of institutions. It's a very large collaboration. It's over 1,000 people, and we all work together on the instruments and the analysis and writing all the papers. And it's a true global community effort to get these results out. Okay, and I'm just going to conclude saying, I hope I've given you some sense. The era of gravitational wave multi-messenger astronomy has arrived. It's here after a century after the predictions. We're now well into this new field. LIGO, Virgo, and Kaga, which is a Japanese detector, are expected to turn back on in about 18 months. It's very uncertain due to the pandemic at significantly increased sensitivity. So the expectation is many, many more events per year. It should be incredibly exciting. So not only will we get all this, we'll really start to nail down these populations, and is the population evolving, and what are the properties, what's the mass issue, all these things. But hopefully there'll be additional surprises like 1905-21, and we'll just have to wait and see. They turn back on, and this is the way this stuff works. We don't really know what's out there. We'll just start listening, and we'll see what happens. Okay, I'm going to end there.
Great, thank you so much, Dan. It's really terrific. So the first question that we had actually came in the chat from Vignesh, and the question is, how are the bounds on the masses of the individual black holes determined? If you could go into some more detail on that.
Okay, so this is an example of the sorts of bounds that we get. And so just to give you some idea of how we're doing this in the first place. So we have a waveform. You might remember I showed some waveforms in the last lecture. So you kind of see the oscillations, and they get faster and faster and louder, and then they merge. Depending on the mass ratio, you can get shifts in the way that thing evolves. It kind of goes back and forth, and you can look for those modulations. And if you can measure those, you can infer the mass ratio. And there, you have to make a set, so you need to know the mass ratio. This can depend on the spins, can depend on orientation. So there are a lot of different numbers that go in. But when you include all that, you can now try to match it to the data and infer these parameters. For things like when it's a massive binary like this one, we actually measure the total mass quite well. So we know what the total was. It was about 150 solar masses, and that we have reasonably well nailed down. But the individual masses we don't do as well. And so you can see this curve here. So you can see this, the contour here shows the uncertainty, or you can look at these plots. And it's a fairly large uncertainty. Here we're saying that the secondary mass could be anywhere from 100 all the way down to 40. That's a very large uncertainty. So, the short answer to your question is we don't actually measure the individual masses quite well at all. That's something we'd like to do better. The longer answer is, it depends on the priors, and we do this template matching, and we have these families of waveforms. I can talk more about those if there's interest, and we combine that all together, and then we end up with a plot like this. It's a good question, though.
And in a related question, how does the degeneracy between sort of the overall amplitude of the signal and the distance fold into so this would be relevant for the standard Sirens, and I was just wondered how that worked, that you were able to untangle things with a higher total mass versus being nearer.
Oh, great. Yeah. So okay, so that's a very tricky thing. So what you can say is, well, maybe this is a higher mass system, and it's nearby, or it's a lower mass system and it's farther away, but it's being redshifted and looks like a higher mass system, and therefore, how can you disentangle this and get an absolute distance? And what's remarkable about standard Sirens is that actually the redshifting drops out. So you're absolutely right. What you measure when we say mass here, we're actually measuring a redshifted mass. It's a redshifted total mass or a redshifted chirp mass. There's always a 1 plus z in there. And so when we give absolute masses, as we do here, we're assuming we know the distance. But what happens in GR is that you can think of it as you get certain ratios. So for example, in the chirp, you have, the rate, you have f dot, the rate at which it's chirping as a function of frequency. And both of those are redshifted. And you can then, if you like, divide those out and actually break out the redshift and to infer a distance. Another way to say it is what we're measuring is luminosity distance, and there's one factor of 1 plus z there. And you can show that when you actually run through it all, that 1 plus z stays there, and so you just get a direct measure of luminosity. So you're absolutely right. We don't get the redshift. We actually don't know what the absolute chirp mass is. But because we get the redshifted chirp mass or redshifted total mass, and we know how loud it is, we can infer the absolute distance, just not the redshift. It's confusing, but that's the way it works. And if you have more questions about this, I actually wrote a Physics Today article with Bernie Schutz and Scott Hughes, and I encourage you to, we spent some time trying to give ways to see how this works. It took me a long time to kind of really wrap my mind around it, because it's quite subtle, but it's one of the amazing things about general relativity that this is the case.
That's just fascinating. We have another question from Sabyasachi.
Yeah, hi. So my question is, in principle, you would also get neutrino fluxes from these mergers. Now, by just measuring the time lag of the neutrinos, in principle, you could put a upper bound on neutrino masses. Now, do you know if there is the present experiments like IceCube or anything else is sensitive to this?
Right. So that's a great question. And I think you're absolutely right that at least in the neutron star cases, we would expect neutrinos. For the black hole, if you have two black holes merging, there are probably no neutrinos. We don't know for sure. We should keep, looking for correlations. You never know. But probably there are no neutrinos. But if there's a neutron star involved, there probably are neutrinos. And it would be, as you say, it'd be amazing to see that. Or not only could we do time of flight experiments, but it would teach us something again about the equation of state and the details of what's happening. The problem is that these sources are pretty far. So 170817, by our standards, was incredibly close, but it's 40 megaparsecs. And so if you kind of go through the sorts of neutrino fluxes that you might hope for, you just don't expect to detect anything with current neutrino detectors at that sort of distance. And so we have to get sources that are much, much closer, and we just don't expect those soon. So if we did get a binary system, a binary neutron star that was very close, then certainly the neutrinos would be there, and that would be amazing. But I think that's unlikely. The case of supernovae, which we discussed a little bit last time, that's a different thing. And for the supernovae, we do, there would also be neutrinos. And in fact, the neutrinos might alert us, and then we can go back and find the gravitational waves in our data. That seems, more robust. There, the question is, and we had some discussion about, the question is, are there going to be enough gravitational waves? Are the gravitational waves going to be strong enough that we'll see one, in our galaxy, assuming it's not right next door, if it's a few kiloparsecs away, and that's still up for debate. But that's the case where we could hope to have neutrinos and gravitational waves and electromagnetic waves, photons.
Okay, thanks.
Yeah.
I have a question. I cannot raise my hand, but so I was curious to see what you think about the possibility of getting information on the electroweak phase transition from gravitational waves, because there are more and more proposals about that, and I was just curious to see what you think about that, even if it's plausible, or if you think it will be very important and interesting to explore because it's something for which colliders have a hard time, right? So, and it's so important.
So, right. So just so I understand, are you talking about probing that through the gravitational wave background?
Through gravitational waves, yes.
Yeah, but using the cosmic, the cosmic background from the early universe?
Yes, or gravitational waves generated through the collision of phase transition bubbles. So that to study the nature
I see. Yes,
of the
right.
transition. Yes.
Yes, right. So there are clear, predictions. This could be happening, like the colliding bubbles, or even just from the phase transitions themselves. That's something that we would love to detect. And so there are searches that are somewhat targeting that. There are kind of there are searches that target compact binary coalescences. So that's these binaries, everything I've been talking about. And then there are searches which we call burst searches. And those searches are targeting anything at all, just something that's a burst, as in you get some sort of burst of energy, but we don't know what the frequency evolution of that will be. We don't know any of the details. We just know that there's gravitational wave energy in both detectors at the same time. And so something interesting must be happening. And those might give us information about, colliding bubbles or kinks and cosmic strings, or who knows. Anything that produces any sort of burst, we would be sensitive to. Now, my understanding is so far, most of those theories predict, event rates and luminosities that are below the range that we would expect from LIGO. It gets more interesting with next generation instruments like there's Cosmic Explorer and Einstein Telescope. There are instruments that are being proposed beyond LIGO and Virgo, the next generation, what we call 3G, and those get much more exciting. They go to slightly lower redshift, slightly lower frequency, and they're much more sensitive in amplitude, and they end up being sensitive to compact binary coalescent binary black holes through pretty much to the edge of the universe, or close out to redshifts of 5 or 10. They're quite amazing machines, and those start to be very sensitive to these sorts of events in certain monospaces. Even there, it's hard to really put strong constraints. To do more interesting constraints, you have to go to space. And so there's a lot of interest in LISA, which is a space-based observatory, which will launch in the early 2030s. And that will then go to lower frequency and be sensitive primarily to supermassive binary black holes, but also be sensitive to the stochastic background and potentially to bursts in a new regime. And that could be quite interesting. However, even there, we're not quite in the regime we want to be where I think most theorists would expect a detection. So we have to go to slightly higher frequency and more sensitivity. And that's the next generation of space-based instruments, like the Big Bang Observer or DeSiGo. There have been a number of proposals for this. And that's where it starts to get very interesting. And there we have more of a hope of detecting some sort of stochastic background and maybe these additional sorts of sources. So I think that's a long-winded way to say my impression, at least from the gravitational wave community side, is that we're not particularly optimistic that we're going to see anything having to do with early universe, electroweak, or anything like that in the near term. But we're making steps towards being able to make interesting probes, in the coming probably decade or two timescale.
Thank you.
Yeah.
Do you have time for another question? Can I ask you?
Yeah, of course.
So I want to go back to GW 190814. So this mass gap object of 2.6 solar masses. So of course, there is also the constraints that you got from GW 170817, which essentially tells you that neutron stars have to be relatively compact. So the idea that you can get a relatively compact object at the same time that you can reproduce a 2.6 solar mass neutron star certainly has strained the nuclear physics very, very much. And of course, even the electromagnetic signal from GW 170817. I mean, I think there was this analysis from Metzger and Margalit that they feel very comfortable that they have an upper limit of around 2.2. So within the collaboration, is there, I mean, I've heard hints that even the collaboration thinks this might be a very low mass black hole, but I would like to know what's your opinion. Well, I mean, if you have to bet, you will bet for a very, very heavy neutron star or very low mass black hole.
Okay, so I'm just going to speak for myself. I'm not going to speak for the collaboration here, obviously. So yeah, so let's. I would say that I agree with everything you've said. It's hard to imagine a neutron star at this range. 2.6 is really starting to push it. There's only one equation of state, so we don't get to pick and choose equations of states for different events. And you know, the constraints from 170817 are pretty weak, so I wouldn't take them too seriously, but they kind of hint a certain way, they nudge us a certain way, which make, you know, this one harder. It's all under tension, and given what else we know about the equation of state and about the neutron star population, 2.6 seems odd. On the black hole side, there's nothing theoretically, you know, there's no compelling argument, I would say, that says we can't have a 2.6 solar mass black hole. We haven't detected one before, but that there might be selection effects there. So I have no problem with a 2.6 solar mass black hole. And, you know, I've written papers saying, here's why we might not expect it. Here's some theoretical reasons why there might be a gap having to do with timescales for instabilities in supernovae. But that stuff is not that well understood, would be my claim. There's definitely room to adjust things. There are definitely theories which would say there are no gaps, and you could easily make a 2.6 solar mass black hole out of a stellar collapse. So if it, you know, if I were betting, I would bet on black hole, but not that strongly, and I certainly wouldn't bet anything that I really care about. I do think that we'll get more information about this.
Very good.
And so, you know, we should have, you know, close to an order of magnitude more events a year. We'll see more events around, you know, these things are very seldom one-off, right? We should see more events like this. So if we see a case where we have a 23 solar mass black hole and a 3 solar mass black hole, or a 3.5, and there's a whole population, then we'll know those are black holes for sure. At 3.5, there's just, you know, without breaking everything we know about, you know, nuclear physics and everything, you know, those are black holes. And then we'll know this is just part of the tail of that population. But if we don't see that, and instead it fills in at 2.3, 2.2, and then there are a few, and then there's nothing beyond 2.6, then we infer the opposite, and that is a neutron star. And that's, you know, the way we're headed. And that's what's so great. I mean, I can't really answer this question now. It's a really interesting question. But you know, if you talk to me in 2 or 3 years, I think it's very likely we'll know. And I mean, that'll be, you know, amazing.
Yeah. Well, thank you very much. And of course, thank you very much for this wonderful lecture.
Daniel, I have a short question if you have time.
Yes, yes.
So regarding this stochastic murmur that you mentioned about the early binaries,
yes.
In order to detect this, do you need to understand the noise in the detectors, or just correlation between the noises in the different detectors is enough to find this?
Yes, right. So yeah, great question. So the trick there is just as you surmised. If you only had one detector, then you would have to tell the noise from these, this murmur from all the other sources of noise. And that would be very difficult. So the trick here is exactly as you surmised. We have multiple detectors and we look for correlations. So we have noise, but if the noise is correlated among these distant detectors, we infer that that's coming from some astrophysical population, just as you said. And so we're using that to infer this background. That's exactly right. And so it's, you know, it's really those correlations, which you expect to be there, because the gravitational waves from these, you know, these unresolved sources, they pass through all our detectors. We can use that information to identify and separate that out from other sources anyways. Yeah.
Thanks.
Yeah.
I have a quick question about the standard Siren thing. So you explained to us that the 1 plus z drops out when you take the ratio of f dot over f. How about other cosmological parameters like dark energy or, you know, dark matter density distributions and stuff like that along the line of propagation?
Yeah. So the nice thing about gravitational waves is that they just don't interact. So if you worry about, say, direct interactions with dark matter along the line of sight, I think it would be hard to come up with a theory where anything happens.
No, I was more thinking about the gravitational effects.
Right,
Yeah,
exactly. Yeah. So all of those other effects go away except for gravitational effects. And so the way I think about it is those gravitational effects, I'm just going to call gravitational lensing. And you know, anything that kind of affects the propagation just from a pure gravity effect, I can write as kind of a metric effect, and I'm going to call that gravitational lensing. And the issue of what gravitational lensing does to gravitational waves is a very active field right now. Just in the last, you know, months, it's gotten much more exciting. And so there's a lot of work. And now, for example, we're doing analyses, and there's a paper in preparation where we're specifically looking for the effects of gravitational lensing on our sources and to see if we can disentangle those. And there's some very subtle effects. There's a, excuse me, a paper I just put out maybe last month, where this is with a big group, including Bob Wald and Wayne Hu at Chicago, and Maca Lagos, and Jose Maria Esquiaga, postdocs at Chicago. And what we did is we pointed out that gravitational lensing actually violates relativity, in the sense that if you have a source, a binary source, and the gravitational waves are lensed, strongly lensed, you can end up detecting gravitational waves which don't agree with the unlensed predictions of general relativity. So if you're only looking for traditional systems that aren't lensed, you could detect something and say, we've falsified general relativity, it doesn't agree with the predictions of the theory. You have to include the fact that they're lensed in there. And that's something which, at least to me, was not at all obvious. Usually you think of lensing as causing shear, which is not a big deal, and causing changes in how loud something is, but not actually changing the waveform. But we showed that lensing actually changes the gravitational waveform. It has phase effects in different modes, and those add up to actually changing the gravitational waveform. Now, you could imagine other things if there's somehow, you know, coupling with dark matter in certain ways that, you know, causes curvature. You could do other things to the waveform. Whatever it is, you know, the gravitational waves just, you know, they propagate through. So you solve the equations, and whatever comes out, that's what we have to look for. So this is something people are starting to think about a lot more, especially as we go to higher and higher redshifts, and the likelihood, you know, you're sampling a lot more of the universe now with these sources. So funny things could happen. Like this particular case is already at 240 megaparsecs, and some of these other cases now we're at the gigaparsec scale. So this all gets much more interesting.
Very cool. Thank you.
Well, and thanks everyone for sticking around so long.
Thanks a lot. Wonderful lectures.
Yeah, thank you very much for taking the time.
You know, thanks for inviting me. It's really nice.
Well, that was great that you could join us. So thank you so much.
Okay.
Bye.
Bye, everyone.
Bye.
Cheers.
Thank you very much.